1. Introduction to Mars. Mars is the fourth planet from the Sun and one of Earth's closest planetary neighbors. It is called the Red Planet because its surface contains iron minerals that have oxidized or rusted, giving the planet its reddish appearance. Mars is smaller than Earth and has a much thinner atmosphere. Its atmosphere is made mostly of carbon dioxide, with smaller amounts of nitrogen and argon. Mars also has polar ice caps, volcanoes, valleys, deserts, and huge impact craters. The idea of falling into Mars can be understood as an object or spacecraft traveling from space toward Mars under the influence of Mars's gravity. What happens during this journey depends on several factors, including gravity, atmospheric resistance, speed, temperature, and the object's design. 2. Mars's gravity. Gravity is the force that attracts objects toward a planet. Mars has weaker gravity than Earth because Mars has less mass. The surface gravity of Mars is approximately 3.71 meters second squared, while Earth's is approximately 9.81 meters second squared. Mars therefore has about 38% of Earth's surface gravity. For example, if a person has a mass of 60 kilograms, their mass remains 60 kilograms on Mars, but their weight would be much lower than on Earth. The weaker gravity affects falling motion. Near the surface of Mars, an object accelerates downward at about 3.71 meters second squared if air resistance is ignored. Therefore, compared with Earth, the object's speed increases more slowly as it falls. This weaker gravity would also affect astronauts. They would be able to jump higher and remain in the air longer than they would on Earth. 3. Entering the Martian atmosphere. If an object falls from space toward Mars, it does not immediately encounter thick air. Mars has an extremely thin atmosphere, with a surface pressure less than 1% of Earth's average sea level pressure. As the object approaches Mars, it enters this atmosphere at very high speed. The atmosphere contains mostly carbon dioxide. Even though the atmosphere is thin, it still has an important effect. Gas molecules collide with the spacecraft or falling object and create aerodynamic drag. The amount of drag depends on the object's speed, shape, size, and the density of the atmosphere. Mars's thin atmosphere creates a difficult situation. It is thick enough to cause intense heating during high-speed entry, but not thick enough to slow spacecraft as effectively as Earth's atmosphere does. When an object falls through an atmosphere, it experiences air resistance, also called drag. Drag acts in the opposite direction to the object's movement. At the beginning of atmospheric entry, the object may be traveling extremely fast. As its speed increases relative to the atmosphere, aerodynamic drag becomes stronger. On Earth, a thick atmosphere can slow an object significantly. Mars is different because its atmosphere is much thinner. Consequently, spacecraft can continue traveling at very high speeds relatively deep into the Martian atmosphere. The shape of an object is also important. A spacecraft designed for atmospheric entry usually has a broad, blunt shape, because this helps create aerodynamic drag and allows the spacecraft to better manage the heat generated during entry. Eventually, if the object slows enough, other landing technologies can become useful, such as parachutes and rocket-powered systems. One of the most dangerous stages of falling toward Mars is atmospheric entry. A spacecraft entering Mars's atmosphere can travel at several kilometers per second. At such high speeds, the gas in front of the spacecraft is rapidly compressed. This compression causes the surrounding gas to become extremely hot. People sometimes describe this simply as friction with the air, but atmospheric entry heating is more accurately associated with the compression and high-speed flow of gas around the spacecraft. The spacecraft therefore needs a heat shield. Heat shields are specially designed to protect the spacecraft and its occupants from the extreme temperatures produced during entry. Without adequate thermal protection, the spacecraft could overheat, lose structural strength, or burn apart before reaching the surface. After passing through the upper atmosphere, the spacecraft continues descending toward the Martian surface. At this stage, its speed has hopefully been reduced enough for additional landing systems to operate. However, Mars's atmosphere remains too thin for a parachute alone to bring a spacecraft safely to a gentle landing in many cases. The spacecraft's speed, mass, shape, and landing equipment all influence what happens next. A spacecraft might use a combination of heat shield, parachute, radar or sensors to determine altitude and speed, retrorockets, landing legs, airbags, or other impact-absorbing systems. The exact system depends on the spacecraft's size and mission design. The final stage is actually touching the Martian surface. This is one of the most challenging parts of a Mars mission. Mars has a varied surface containing rocks, dust, sand, mountains, valleys, and craters. A spacecraft must avoid dangerous terrain while reducing its speed to a safe level. A parachute can help slow the spacecraft, but because Mars's atmosphere is thin, it cannot always provide enough slowing by itself. Some spacecraft therefore use engines during the final stage of descent. For example, robotic Mars missions have used different combinations of parachutes, rockets, airbags, and landing systems. Future human missions will require even more sophisticated technology because humans need a controlled and safe landing environment. A successful landing means the spacecraft reaches the surface with enough structural integrity and remaining resources to begin its mission. Falling into Mars is not simply a matter of an object dropping toward the planet. It involves a complex interaction between gravity, speed, atmospheric density, aerodynamic drag, heat, and landing technology. First, Mars's gravity pulls the object toward the planet. As the object approaches Mars, it enters the thin atmosphere at extremely high speed. Atmospheric interaction produces drag and intense heating. A heat shield protects the spacecraft, while parachutes and other systems reduce its speed. Finally, rockets or other landing technologies help the spacecraft reach the surface safely. The process demonstrates why landing on Mars is much more difficult than simply falling onto a planet. Understanding these physical processes is essential for designing spacecraft that can safely reach Mars and eventually transport humans there.